Hello everyone. So welcome to physics classes by Sarabdeep Kaur Sidhu. Today's our topic is Michelson interferometer. So it's a very important topic for exams. First of all, what is it? So it's an instrument or a device which is devised by Michelson, in which the amplitude of a light beam from an extended source. Which source is used? Extended source is divided into two parts. These two parts having equal intensity by partial reflection and refraction. And the parts then reunite. These two parts then reunite to give interference pattern. It was used. What is its use? It was used to detect the motion of the earth through ether is used as a medium, or to detect the hypothetical ether as a medium through which light waves were supposed to propagate. Yeah, so we can say that it is a device to exploit the interference of light for some useful scientific purposes. Then second part is, what is its experiment setup? How we can experimentally set up it. So it consists of, this is a diagram showing the experimental setup. And it consists of two well polished mirrors. One mirror is this one, and second mirror is this one, M1 and M2. This is M1 mirror and this is M2 mirror. Clear? And these two mirrors are placed at this mirror and this mirror, these are placed at 90 degree with respect to each other. And half silvered glass plate, this is the glass plate equally inclined to the mirrors M1 and M2. Equally inclined to the mirrors is M1 and M2. Here this glass plate, this is silvered, we can say this is the glass plate, and this is half silvered plate. This is clear. And small telescope, here is a telescope which is focused at infinity to see the interference pattern. Clear? This is the experimental setup of this. Now how it works? So the experimental setup of Michelson interferometer consists of two mirrors M1 and M2, which are 90 degree to each other. Mirrors are at 90 degree to each other. Clear? First point, each other. Okay, well polished mirrors these are. And the glass plate, GP glass plate, that is half silvered glass plate equally inclined to mirrors M1 and M2. It is also, glass plate is also called a beam splitter. Because the parallel beam of light obtained from this extended source, so the parallel beams of light which is obtained from this extended source of light, when these are inclined on this glass plate, then this is splitted into two beams of almost equal amplitude due to partial reflection and refraction. Clear? Due to partial refraction and reflection, the refracted beam goes to mirror M1 and is incident normally on it. So from the mirror M1, the incident beam is reflected along the same path, and after reflection along the same path, and this is incident on this glass plate. Clear? On this glass plate GP, from where it is reflected downwards. And the reflected beam, second beam, refracted beam, that is the first beam. This is the reflected beam, second beam, this is the second beam, goes to the mirror M2 and is incident normally on it. from the mirror M2 the incident beam is reflected along the same path, this is the same path, clear, and is then transmitted through GP glass plate through GP and join the beam reflected from M1. The beam reflected from M1 and from this M2, then these two are rejoined. Clear? The beam, third beam, this is the third beam, this one, this is the third beam. Third beam contains light reflected from mirrors M1 and M2. The reflected beam 2 passes, this beam 2 passes through the GP thrice. So reflected beam, that is the second beam, this second beam, this one, this passes through GP thrice, but the beam 1, this beam passes through it only once. So to compensate for it, the plate C is placed parallel to GP in the path of beam 1. Okay, so this is the additional plate, okay, to compensate that. Clear? The plate C is made up of the same material as that of GP is made. Okay, and what is the use of this plate? The use of this plate, C plate. What is the use of C plate? The use of the plate C is all the more essential when white light is used. So in such a case, the optical path lengths of beam 1 and beam 2 must be exactly equal. Okay, so beam third, which is beam third, this is beam third, consists of light reflected from M1 and M2. The optical paths of two parts of this beam 3 can be varied, and they interfere to produce interference fringes. I am repeating again. The optical path, this is the third beam, this one is the third beam, here. So the optical, you can say the interference pattern is fringes is produced due to the optical paths of two parts of the beam 3. So the optical paths of the two parts of beam 3, this one 3 beam, can be varied, and they interfere to produce interference pattern or interference fringes, which can be seen by a eye in the path of the beam. Okay, we use here a small telescope to see the interference pattern. So this is the way how Michelson's interferometer works. Clear? See, then I hope this part is clear to all of you. Then is the formation of fringes. How now fringes have formed? Clear? How we can find the shape of the fringes? How we can find the shape of the fringes? Okay, ji? How we can find the shape of the fringes? These are determined by the mutual inclination of the mirrors M1 and M2. M1 and M2 are 90 degree inclined 90 degree to each other. So optical system, this is the optical system that is as shown in the figure. This is the construction of optical M1 M2 mirrors, how GP is formed, how here is a eye. Okay, these are the optical axis. Clear ji? So consider an equivalent optical system. So it is the optical system having a single optical axis. So this is optical axis which is perpendicular to mirror M2. This optical axis is perpendicular to this mirror M2. Clear ji? Here the mirror M1 is replaced by its image. M1 mirror is replaced by its image, that is M1 dash. Clear ji? In the mirror M2. Clear? Also the source is replaced by a source S dash. So this is the source replaced by a source S dash in the same mirror, that is M2. Now P is any point. P is any point. This is the point P. This point P is any point on the source image S dash. Clear ji? In the P is any point on the source image S dash, and a ray of light inclined to the optical axis optical axis at, this is the ray of light inclined to the optical axis, making an angle theta on mirror m1 and m1 dash and m2 dash. The reflected beams appear to come from the virtual images m1 p1 and p2. Clear? So the reflected beams, clear ji? And of the source s dash in the mirror m1 and m2. So there are the virtual images of this source s1 s dash. Virtual images, there are the virtual images of this source s dash on the mirrors, in the mirrors m1 dash and m2. So if the separation, this is the d, small d, this small d is the separation between m1 dash and m2. Clear? And then this is the separation between m1 dash and m2. If separation between m1 dash and m2 is d, this d, then what is the separation between s1 dash and s2 dash, which are the virtual images of s dash? That is the 2d. Clear ji? So that will be 2d, this one. ठीक है जी? So this is p1 point here, I forget to play p1 p2. So 2d is the separation between s1 dash and s2 dash. Hence the optical path difference between the reflected beam, between the optical path between the reflected beams going to the eye, will be delta is equal to 2d cos theta. Clear beta? So this is the explanation of this diagram. Delta is equal to 2d sin theta, and the total path difference between the interfering beams will be delta p, and that is equal to delta plus lambda by 2. We know this. Okay ji? And because we find that the beam 1 experience a reflection at the denser medium from the plate GP, but the reflection of beam 2nd from the GP at rarer medium. So additional path difference of lambda by 2 that is added here. ठीक है, is introduced in the beam reflected from the mirror m1. Clear ji? Hence the path difference between the interfering beams will be delta p is equal to delta plus lambda by 2, or delta, we know that 2d sin theta, 2d sin cos theta, not sin theta, cos theta plus lambda by 2. ठीक है जी? Hence we will obtain a minimum in the interference pattern. So there is a minimum in the interference pattern, and delta, for minimum, delta p is equal to 2p plus 1 lambda by 2, 2p plus 1 lambda by 2, and 2d cos theta that plus lambda by 2 is equal to 2p. Put the value of delta p from here, 2p plus 1. So from this 2d cos theta that is equal to p lambda. ठीक है? And when there is a maxima, then 2d cos theta plus lambda by 2 that is equal to p lambda. Then 2d cos theta is equal to 2p minus 1 into lambda by 2. ठीक है जी? Then is the circular fringes. Circular fringes, the fringes of equal inclination. Fringes are localized at infinity and can be seen by eye or telescope focused at infinity. So in this case, there are three cases if d is equal to 0. When d is equal to 0, then what about delta p is equal to 2d cos theta plus lambda by 2? So from this, when you put d is equal to 0, delta p is equal to lambda by 2. So central fringe, what about the central fringe? When delta p is central fringe is, that will be dark. Clear? When delta p is equal to lambda by 2, d is equal to 0. And second case, first case d is equal to 0. What about the second case? Theta is equal to 0. When theta is equal to 0, then delta p is 2d cos theta plus lambda by 2 cos 0 that is equal to 1. Then from this we have delta p that is equal to, we get delta p is equal to 2d plus lambda by 2. Clear? And when d, we have a d, when suppose we have d is equal to lambda by 4, when we putting d is equal to lambda by 4, what about delta p that is equal to lambda? So central fringe becomes a maxima and minima alternatively. So in this case, clear ji? And case third, if we look at the fringe pattern obliquely that is inclined to the optical axis at a certain angle theta, we observe the circular fringe, say a minima, for which d decreases, and if d increases for this, d decreases, d increases, and if d increases, then 2d cos theta also increases. So 2d cos theta is equal to p lambda. But we know, but for a fringe of pth order, it should remain equal to p lambda. That is, then it implies 2d cos theta, that is equal to constant, or we can say cos theta is inversely proportional to 1 over t. So this is also important concept. Third case, so from this, if d increases, the fringe of pth order cos theta decreases or increases. In other words, as one of the mirror is listen carefully, so in other words we can say that as one of the mirror is moved parallel to itself, or the fringes appear to expanding outwards, and the central fringe becomes a maxima and minima alternatively. Clear? Then is the localized fringes. So there are three diagrams here, A, B, C. We have discussed in the previous section that M1 and M2 are perpendicular to each other. M1 and M2, they are perpendicular to each other. Okay? And if we say if they are inclined to each other, then what will happen? If angle is less than 90 degree. Okay? The air film between, then at that time the air film between M1 and M2 as shown in the figures becomes wedge shaped. This is wedge shaped. This one. Okay? And we get localized fringes of equal thickness located between S1 dash and S2 dash, as we have seen in this figure. This is S1 and S2. Clear? I am repeating again what are localized. If angle is not 90 degree, it is less than 90 degree, then the air film between M1 and M2, then air film between M1 and M2 becomes wedge shaped. Okay? And at that time we get localized fringes, and we get localized fringes of equal thickness located between S1 and S2. Okay? So these diagram shows that. Clear? So see, when M1 dash M2 dash cut each other, then straight, and when they cut at this point, then fringes are changes. Okay? So the fringes are straight, perfectly straight here, they are perfectly straight when M2 actually intersect M1 and M2 dash actually intersect in the middle. In other positions, say shape of the fringes that are curved, this is curved. Clear? So they are curved and are always convex towards the thin edge of the wedge. Clear? So these types of fringes are not observed for large path difference. Then the order of central fringe, if theta is equal to 0, fringe is dark, as we have discussed in the previous. So 2d cos theta is equal to p lambda, 2d is equal to p lambda, p is equal to 2d by lambda. So we can find out p and lambda in this way. Clear? Then what are the applications of this? First application, and this is used to find out the determination of wavelength of light. Wavelength of light for central dark fringe, we have studied theta is equal to 0. Then 2d cos theta is equal to p lambda. So lambda is equal to 2d by p. So in this way we can find out this p. Clear? And if we have two mirrors, then we can also have suppose करो geometrical separation between M1 and M2 dash. Okay, for the pth order dark fringe we can say be D1, that is we are taking D1, and for pth fringe the separation is D1 between M1 dash and M2, and for P plus suppose कर लो P plus mth fringe, the separation between them is D2. Then what is the relation? We can say 2d1 that is equal to p lambda, and 2d2 is equal to p plus m into lambda. If separation between m1 and m1 dash and m2 for pth fringe is d1 and for p plus mth fringe is d2, then from these two relations we can find out lambda, and lambda comes out to be 2d1 minus d2 over m. So in this way we can find the wavelength. Clear ji? Then we can also find out the small differences in the wavelength with the help of this Michelson interferometer. Clear? Then also we can find out the refractive index of the material, and that will be equal to m lambda over 2t plus 1. Okay, and last we can find out the thickness of the transparent sheet, and that is t is equal to p lambda over 2n minus 1. So in this way these are the applications of Michelson interferometer. We will discuss in detail if you want in the next video. Thank you very much.